All right, so we've completed section 6.1. I've got a nice introduction to counting techniques. We had things like the sum rule and the product rule and the subtraction rule. So what we want to do now is I'm going to skip section 6.2 for the moment. We're going to come back to section 6.2 next week. But I want to skip ahead to 6.3 because 6.3 introduces some more counting techniques and strategies and formulas and things that you're going to want to use on your assessment. So in the first example, let's take a club of 30 people. So maybe this is like the math club. We've got 30 people in the math and computer science club. That club needs to select some officers. We have a president, a vice president, a secretary, and a treasurer. So of this club of 30 people, we need to select 4 officers. 1, 2, 3, 4. And they are named president, vice president, secretary, and treasurer. The question is, in how many distinct ways can we do that? In how many different ways can we select our 4 officers? Well, the officers, the positions, like the roles that they play, are different from one another. So if I came along and I said, let's have person A be the president, and person B be the vice president, person C be the secretary, and person D be the treasurer, that would be a different way of selecting than, for instance, having A be the president, having C be the vice president, having B be the secretary, and having D be the treasurer. So just swapping the B and the C here, swapping the roles of those 2 people, it's the same 4 people, but that would count as a different selection of officers because we have persons B and C playing different roles, right? They're serving different tasks. So the question is, in how many different ways can we do this? Now, we could select a different set of people entirely. We could have selected like D, E, F, and K as our 4 people, and they could have been selected in any possible order, right? So the question here is, how do we do this? How do we count the number of different ways to do this? Well, we can do it with the multiplication rule. Let me line this up again. We have we have president, vice president, secretary, and treasurer. 1, 2, 3, 4 positions, and there are 30 people. So we could select the president first and say there's 30 different people who could select the president, who could be president. Once we've selected someone to be president, that person is now used up. They can't also be the vice president. So when we choose the vice president, now there's only 29 options. And then when we choose the secretary, now there's only 28 options. And when we choose the treasurer, there's going to be only 27 options. So multiplying those together using the multiplication rule, we get our answer, which is, it's a big number, 657,720. That's the total. Here we go. Now, it doesn't matter what order I selected those in. Like, we could have selected the secretary first. We could have said, let me just draw this out in another way. We could have said, let's elect our secretary first. There's 30 options for that. And then we'll select the president, 29. And then we'll do the treasurer, 28. And then we'll do the vice president, 27. And it doesn't matter what order I do those in because multiplication is commutative, and I end up getting the same answer anyway. So the order in which we selected them doesn't matter. All that matters is that these 4 different positions are distinct from one another. So swapping the people we select for 2 positions is going to produce a different outcome. And so what we're doing is counting the total number of possible outcomes. All right, let's formalize this idea. What we're doing is counting what are called R permutations of n objects, where R is a number and n is a number. We want to have 0 less than R less than or equal to n. So these are 4 permutations of 30 people. That's what we're talking about. Normally, a permutation of 30 people would be an arrangement of all 30 of them, but a 4 permutation is just taking 4 of them. It's like selecting 4 is an ordered selection of 4 people from the 30 possible people. Okay, so we're selecting 4, and also we're doing it in so that the order matters, right? Because remember, swapping the B and the C resulted in a different outcome. So in that sense, order matters. Okay. And the number of different ways to do that has its own special notation. It's called P, N, R. So let's make a permutation out of n people or n objects, we're going to select r of them. The other way to write that is npr, like this, with like a little subscript on the left and subscript on the right. npr. This is what it looks like when you do it on like a TI-84. And the formula for that is n factorial divided by n minus r factorial. Where does that come from? Well, this, up here, we did 30 times 29 times 28 times 27, right? Well, this is like taking 30 times 29 times 28 times 27 times 26 times 25, all the way down to 1, and then dividing that by 26 times 25 times all the way down to 1. Because here, the 26 would cancel, the 25 would cancel, everything would cancel down to the 1, whatever. The 1 doesn't really, well, the 1 can cancel, sure. And what's left over is just these ones, right? So what you can see here, this ends up being the same as saying, let's just do 30 factorial divided by 26 factorial. And the first 26 numbers all cancel out, and leaving us with just 30 through 27 that are multiplied together, right? That's the idea here. And so if you do n factorial divided by n minus r factorial, the n minus r factorial is actually going to cancel out, leaving you with n times n minus 1 times n minus 2, all the way down to like basically the first r factors in that product would be left over. So that's how you do permutations, in the more general type of permutations where this is like a sub-selection. General guideline about this, use this when the order matters, right? So president, vice president, secretary, treasurer, the order of the people we select matters, right? Like putting the people in a different order produces a different outcome. Just want to note real quick that this notation is consistent with the factorial like formula for calculating the total number of permutations of all n people. That would be PNN. Right? If you're going to take a permutation of all n objects from the set of n objects, you stick n in for r, and you get 0 factorial in the denominator. And we define 0 factorial to equal 1, basically because if you have no objects, there's one way to arrange those no objects, which is not at all. So the definition of 0 factorial is 1. Okay, we just take that, we're going to take that for granted. And that gives us n factorial. So, okay, now let's do a second example. Spin off on this first one, right? Instead of selecting officers, this time we're just going to select a committee of 4 people. The difference between this and the previous version is for the 4 committee members, it doesn't matter what order we put them in. So we could do, so saying A, B, C, D, and A, C, B, D. In this case now, those are the same committee. It's the same committee, right? The same 4 people. It doesn't matter what order they're in this time. If it's the same 4 people, it's the same outcome. So when you change it like that, so that instead of it being an ordered selection, if it's now an unordered selection, that's called a combination instead of a permutation. So this is an R combination of n objects. It's an unordered selection, right? That being the key word there, unordered. A selection of R objects from a set of n objects. And we use the notation to count the number of different possible ways to do that, CNR or NCR. And it's almost the same, okay? This is almost the same. It has the n factorial divided by n minus r factorial, which is identical to permutations, but then there's also a factor of r factorial in the denominator. So this is the same as saying, let's take all the permutations, P and R, and then divide by r factorial. And the reason for that is basically you're removing the ordering. You're removing the ordering. So like with these 4 people, we had 4 factorial different arrangements of the people A, B, C, D. So forget this version. Just talking about the people A, B, C, D, there's going to be 4 factorial different ways to arrange those people. But when you're talking about a combination instead of a permutation, now all of those different arrangements are all counted as the same outcome. So that entire group of 4 factorial different possible permutations, those are lumped together into one. And every single possible different combination of people has 4 factorial different permutations that are going to be lumped together into one. So we're taking it's like you're taking the number of different permutations, dividing it by the 4 factorial, so that you're taking the groups of size 4 factorial and counting how many of those there are. And so dividing out by the number of ways to arrange those people makes it so that the arrangement order no longer matters. That's not what we're counting, and that gives us the combinations formula. So yeah, I just wanted to explain where that formula comes from. That's pretty cool. So that's that. We'll leave it at that for now. In the next video, I'm going to explain a little bit more about that and an alternate notation for this one.